We've got Tembi and Tom, and they hold each other and they skate along a smooth surface. They have a common forward velocity of 5 meters per second. Then Tembi gives Tom a push forwards, and he moves with a uniform velocity of 6 meters per second. What's the velocity left over for Tembi is going to end up being our question. But first we have to state the law that would help you calculate Tembi's velocity, and it is the law of conservation of momentum. What does it tell me? It tells me that momentum before is equal to momentum after. We have got their combined masses before, which is fairly unusual but not difficult for you to deal with. They have a combined velocity, and you have got 54 times some or other velocity of Tembi's, v, and that's added on to Tom's mass multiplied by his velocity. And when I work that all out, I get 3,59 meters per second. It's a velocity that they want, so you've got to give it a direction, and that's going to be forwards. Now they want the total kinetic energy of both before and after that separation. So let's work that out. From that, we're obviously going to have to decide whether we were able to conserve kinetic energy or not. So the EK before is equal to a half of the mass of the two together times the velocity squared, and after it's equal to a half of both their velocities separately and speed and 3,59 squared plus half of who is a Tom, 76 and 6 squared. My squares aren't looking very good, but anyway, you need to square both of those numbers. When I add it all up, I get 1625 joules, and I get 1715,98 joules. Now, where did this extra kinetic energy come from? Because obviously, weirdly, their energy has increased. Obviously, Tembi added some energy to that because of the push that she gave. So she gave energy from her arms into that system. We've now got a 0,03 kilogram bullet. Nice for them to have converted it already for you, yay. It's shot horizontally with a certain velocity into a block, and we've got the mass of the wood, and it's suspended, so it's standing still to start with. After the impact, the bullet gets stuck in the wood, and they both swing up 0,8 meters. So what was the velocity of the block and the bullet after the impact? So I can work out the potential energy over there and the kinetic energy in that position. So we're only going to look at conservation of energy at the bottom, at least at the beginning. And we're going to say the EK at the bottom is equal to the EP at the top. And that's a half mv squared is equal to mgh. Good news is I can cancel the masses. Yay! And I'm left with a half. I have no idea what the velocity is, but I do know I've got 9,8 multiplied by 0,8. And therefore, when I square root and everything, I land up with 3,96 meters per second, and it's going to go towards the right. It's about 4 meters per second, close enough. The initial velocity of the bullet, I now need to look at conservation of momentum. So the momentum before the collision is equal to the momentum after the collision. And after the collision, I've got their combined mass, which is 1,47 plus 0,03, and that turns out to be 1,5 multiplied by their velocity together, which is 3,96. And my momentum before the collision, the block was still, so I only have to care about the bullet, 0,03 multiplied by some or other velocity that I do not know. And when I rearrange all of that, I am going to land up with that velocity that I was interested in. It's actually an initial velocity, is going to comes out to be 197,98, or rather 99. So it's as close as anything, 200 meters per second. And again, it's to the right because they're asking me for a velocity, so I must give a direction. I've got a high-speed camera, and it's used to photograph a mechanical golf club that is testing a golf ball. The camera takes 1,000 pictures each second. Now, we've worked with those direct measurement video. So we know that if we're getting 100 pictures per second, the time between for each photo, and it's going P, Q, R, S, T, U, and obviously there's a collision in between, and therefore we are getting 1,000th of a second between that time and that time, that time and that time. The vertical lines on the photograph are 1 centimeter apart. It doesn't look like that. It looks like they're millimeters apart, but actually what they're telling us is that there are 5 centimeters in between there. It's just been zoomed down. The diagrams show successive photographs, P, Q, and R, before, and S, T, and U after. What is the time interval between successive shots? Well, if it's 1,000 pictures per second, it's 1,000th of a second, which is 0.01. What is the speed of the ball after the collision? So now after the collision, I need to look at the ball, and I need to choose a point. So I'm going to go right in front over there, and I'm going to say that after the collision, I could say 21, or if I wanted to, I could go to the back of the ball, and I could say 17. I'm going to go at the back of the ball just because I've got that all calculated out, and I can also go to the back of the ball at point U, and I can go 19. So between here and here we have got 2 shots, and therefore the time is 0.002 seconds, because the time between one shot is 0.01. There aren't 3 spaces. Remember, it's 1 space, 2 spaces, and that's how far we've gone. So let's see what's happening. So I'm going to say velocity is equal to change in displacement, which is going to, sorry, this isn't 19, it's 29. It's going to be 29 minus 17, which is equal to 12 centimeters. But 12 centimeters is actually equal to 0.12 meters, divided by a time of 0.02 seconds, and that turns out to be 60 meters per second. They then tell me the mass of the ball and the mass of the club, and we need to show that momentum has been conserved in this collision. So it's a bit of a mission from here onwards. It takes quite long because I need to work out the momentum before of everything, the momentum after, and all of that sort of thing. So let's see what we get. The first thing is that before, I have got the club moving, and it is going, V is equal to distance over time, and I can take a look at this club and I can say that it is, the back end is at 23 over there, and over here it is at 13. So 23 minus 13 is going to be 10 centimeters, which is 0.1 meters, and that is divided by the time of 2 spaces, so it's 0.02 seconds. 1 hop, 2 hops in terms of time, and I land up with 50 meters per second. The ball is standing still. So the momentum of the club before is going to be 0.27 kilograms multiplied by 50 plus the momentum of the ball, which is 0, and my total momentum before is going to be 13.5 kilogram meters per second. Then afterwards, we are looking at the club. Well, we know the ball. We've already worked that out. The ball was going at 60 meters per second. To work out the club afterwards, we are going to say velocity is equal to displacement over time, and the displacement of the club is going to be from 11 to 19. So it's 19 minus 11, which turns out to be 8 centimeters, which is 0.08 meters, divided by 0.02 seconds, and that is equal to 40 meters per second. And therefore, if I'm calculating the momentum, I have got total momentum of the club is 0.227 multiplied by 40, plus the ball 0.045 kilograms multiplied by 60, and I land up with 13.5 kilogram meters per second, which is just wonderfully idyllic, and therefore momentum was conserved.